So we're switching gear. Last time on Tuesday we talked about how the metals will crack. We talked about brittle fracture. We talked about low temperature effects, especially with steel and BCC metals that are not face-centered cubic. Essentially, most of them end up having reduced ductility at low temperature. We covered a little bit of fatigue. That was the cyclic application of load, and I have the boat shaft example for that. I explained to you a little bit how to look at the fracture surface. One of the first things that is good to know when you have a fracture is whether you had a pre-crack, whether it was just completely tearing and opening up the material, or whether you had something preceding it that essentially reduced the strength. Because once you crack the material, you're not going to change the shape anymore to break it. It's really going to localize in that area of the tip of the crack as far as the deformation. There's much less energy involved in breaking something that's already pre-cracked, regardless if it's steel or plastics. With plastics, there's a lot less energy involved in breaking them, even if they just have notches on them. And it's one of the limitations in terms of saying, I'm going to take this piece of plastic and I'm going to take it something very reliable. Because if you scratch it with something sharp, all of a sudden you lose the skin effect. The skin of the plastic from the molding process is typically stronger than if you machine the part. So what happens is, if it's injection molded, all the molecules line up, and on the surface you're going to have essentially a kind of a little bit of a fiber structure, and it's going to be much better than if you take a big piece of plastic and machine it out. In that case, you have a lot of cut material on the surface as opposed to more of an arranged structure. So I'm going to circulate this one because I think you all know this, but it's very cheap to make parts out of plastic. This one here is a filler neck for the jet ski. So all at once, you make this part, and then multiple injection ports. I haven't looked at it recently, but so you insert plastic from different direction into this mold, make the part, and you have cooling in the mold, and so it comes solidified very quickly. And then you move on and make another one, and you can make very large volume at, I'm not going to say essentially no cost, but once you have everything set up, there's very little material cost involved, and there's very little time or energy expense in doing it. So you have, at the same time, one type of thread for putting the cap on the exterior, and this thread was just to secure it to the hull. And that's the hose that came with it. You do need to be careful when you're dealing with something like this, because there are a lot of stress risers, a lot of corners. So in this case, the hose is relatively large, and you can think that over time, if it's not all perfectly aligned, that you can have cracking starting around one of the stress concentration area. It's not necessarily from vibration from using it. It could be just a set load from the things not being perfectly aligned between the tank and that port there. So there's some limitation in terms of saying, okay, I'm going to use as much plastic everywhere in a structural application, because it's not as forgiving as steel is. Steel, if it's not exactly where it's supposed to be, a lot of times you deform it locally a little bit, and it will release the stresses, and then you're good to go again. This type of material, a plastic, will keep track of how long you're loading it in each direction. If you're loading it for a very extended period of time at a high enough load, you're likely to just start a crack under constant load. So it's not just a question of For metals at ambient temperature, you need fluctuation if you're going to start a crack at low load. With plastic, it can happen even if it's just a steady load. That's one of the issues. And other issues with plastic is joining. And there are techniques now to fusion well different pieces of plastic together, but you end up with having to control it, and you can't. It's like with metal, you can't get exactly the same thing as if you plastically deform it, extrude it, or make shapes out of any deformation processing technique. Regardless of all of this, it's used a lot. And I do want to give you a few examples. A lot of pipe fittings in homes and like commercial buildings will be plastic. A lot of tubing, the advantage is as opposed to steel tubing or copper tubing is you can, if you have a flexible pipe, you can turn around instead of having to make joints every time that you go from one place to the other in a building. For a large infrastructure, so here it's just a drainage application. It's cheap and it's not going to corrode in a way that steel will corrode. Now, as you can see, it's out of shape here. It's not round anymore. So the issue of the behavior under load is one of the main drawbacks for using it for water distribution, for gas distribution. They use a lot of polyethylene, and they use a high enough density that they control the creep, so the expansion of the pipe over time, so it still doesn't break or doesn't change dimension too much in a 20, 30-year life. And we'll go a little bit through how they arrive to this. Here I'm showing just a little cover around a fan for the engine block in cars. So cars have progressively been built with more and more plastics for reasons of weight and cost, primarily. Now, this one particular situation, there'll be some heat, so it makes a difference if it's really going to be just ambient temperature or if it's going to go all the way to boiling temperature for water. The creep behavior is going to be very different, and you have to be careful with that. So let's go ahead and first talk about creep. It's something that I've not mentioned when we were talking about metals and how they behave, but I wanted to bring it back here and sort of treat it one after the other. So we'll do metals first and then talk about plastics. If you take a metal like the nickel superalloys for turbine engine blades, and you heat it up above half of the absolute melting point temperature. So say if you melt at 2,000 degrees Kelvin, above 1,000 degrees, you could start having some creep taking place. What happens is you load and you get that little elastic deformation, so that's epsilon 0 here, and then over time you keep adding up strain. So in this schematic here, it's broken down for us in 3 different steps, where this first one is the elastic strain. Then you have what they call the transient creep. So this is something that goes fast initially, but then as you go, you exhaust the possibility of having that little viscoelastic deformation. And then most material, if they are susceptible, they have a time dependency. If you wait long enough, you get this more of a steady state movement inside the materials. It's a viscous creep type behavior. And most material will show it right from the beginning. So there will be one process behind the whole scene that's actually happening at a constant rate. But if you have another transient creep on top of it, you don't really see it. So what's prevalent is the faster. That's where you see the curve tapering off here. But in reality, there's also viscous creep all the way from the beginning. It's just not noticeable. So on the overall curve, with metals, eventually you're going to start forming void. You're going to start degrading the microstructure, and your rate's going up. But that's not necessarily, most of the time, it's not related to creating new ways of deforming. It's more becoming into really degradation, creation of voids and coalescence, a little bit like we talked about in the ductile fracture. So it's accelerating a little bit at that point. It's a typical curve. What happens with turbine blades is they design them to allow a certain amount of elongation during service. And the way they built this is in the shroud that's encasing them, the interior surface of that shroud is relatively porous and essentially gets worn out as the blades expand. They decided to do this to make sure they don't have a whole lot of loss, so air flowing between the two components. So instead of creating a gap for the initial as-built engine, it's almost in contact when it's all working, and then over time it's just eating up the shroud to account for the expansion of the metal. Well, the creep. Let's use the proper terms here. So it doesn't happen with metals in a lot of applications, although at Cambridge University in England, if you go around and you see the old pipes, they sag. And it wasn't the case when they put it up, but it's essentially an example that lead at ambient temperature will creep. Tin can do it a little bit. It's easier if it's a little hot. So it's related to the melting point of your alloy. There are multiple mechanisms by which the metals creep. Obviously, I'm not expecting everybody to remember it, but I'll talk about it a little bit generally. If you're at low temperature, it's all related to that thermal activation that I talked to you with respect to dislocations. And we talked about it, with the phase transformation. I think we talked about it quite a bit actually in this class. So if you're at very low temperature, you want an easy path because you can't move the atoms a lot. So you're going to try to have the movement of the material through the grain boundaries. It's slow because you only have so much grain boundaries per volume of material, but it doesn't require a whole lot of energy, and it just happens quickly. So you start with grains that are, say, equiax, and then eventually they become a little more elongated as the material moves from the side to the tip of it. As you start going to higher temperature, soon enough you're going to be able to move dislocations. So you can have a positive and a negative dislocation. They're going to combine a little bit, like I said, would happen when you apply 200-300% strain at ambient temperature. When you heat it up, now all of a sudden things start moving. So that's your dislocation creep here. If you're high enough temperature, you can have the grains moving relative to each other. It's not something that we see that we want to do a whole lot in practice, but at the same time, it can be used in processing in terms of reaching superplasticity in conditions where the material, you're just able to deform it and it heals itself as you go. So there are a lot of different aspects of creep of metals, but it just gives you the general idea is the higher the temperature, the easier it is to move a lot of things together. That's just another view of it. So we're looking here at the stress level as opposed to grain size. So there's an effect of grain size, big surprise about all of this. Super alloys is essentially you try to make each grain so big so you don't have that issue of having the diffusion going preferentially. And inside each grain, you try to have as many second phases, so sort of precipitates that prevent the movement of dislocation as well. So it almost looks like a composite when you look at it under the microscope here. So there's an oxide dispersion, and you can have it as much as 30–40% of the volume, and it's all part of the same crystal or arrangement. There are some differences, obviously, when you go from one phase to the other, and that creates friction for the dislocations. All right. Any question about creep of metal? I remember my early learning of polymer science and thinking, like, why would I ever want to know the difference between polyethylene, polycarbonate, and all these guys? Well, it's all just a question of ranking them by size. So polystyrene is an example of a material that's hard to deform. It tends to break easily, and it's just related to having that benzene side group here on the chain. So you have a large side group on your main molecular chains. It's very difficult to have one chain past the other. That's just about all you need to know. And if you branch the polymer, if you cross-link it, anything that you're going to do to prevent the movement of one big molecule with respect to the other reduces your ductility. Sometimes it's a good thing, sometimes it's a bad thing. It really depends on your application, and we're going to go through that in more details. So you have here polyethylene. That's one that is relatively soft at ambient temperature, and you go towards a little harder because all of them, as you go down here, you have bigger and bigger side groups. What else there is to say about these here? Most of the time, you can also change the properties by the length of these chains. It's one very important parameter. If you tell me, oh, I'm going to make it out of polyethylene, well, the first question I need to ask you is, okay, so are you going to go with low density, high density, ultra high density? Because it's affecting how much you can move one chain to the other. And we'll go through that structure in a fair amount of details. A lot of polymers, so polyamide, nylon, polyethylene, polypropylene will crystallize or partially crystallize. So essentially, as you cool them down, eventually you start forming crystals in the bulk of the material. It tends to grow in parallel with crystal and an amorphous zone in between, because things don't all line up, and whatever doesn't fit in the crystal gets pushed out into that amorphous layer. So it's growing in parallel a little bit like our perlite and other things that we've looked at. And then eventually it reaches the other nucleus, and you end up with something that looks a little bit like grains, except that we call them spherulites, and they have all that fairly complex arrangement. Now, when you deform these semi-crystalline polymers, you have an effect of this structure. A lot of times it can be a beneficial effect, sometimes it's not. And on the very basic level, if I cool down very slowly here, I'm likely to form layers of crystal that are thicker, and I can have a higher percent of crystallinity. But at the same time, these large pieces in the microstructure of my polymer are going to reduce ductility. It's really not uncommon. If you have these ferrites really very thick, they just become a very rigid block against the amorphous zone that is softer, and you have a preferential site for deforming and eventually starting to crack. So we're going to stay here at the microscopic level because I think it's useful to understand if I cast nylon, for example, to make a rope, I get the spherulites first, and then when I deform it, when I draw it, I get rid of it. I break down the original as cast microstructure, and I line up all the different crystals, and they call it here fibril structure. And it's one of the reasons why polymers will have very low hardening initially, and then the hardening goes up. So if I take a tensile specimen, the main difference with metal is the necks tend to be stable. So if I start like here, I will form a neck in a certain location. So say I just make it happen here. Both sides. So it's a large reduction in area. But that neck is going to grow over time, and I'll end up with specimen that is sometimes 5 to 6 times longer than what I started with, and then it'll snap on me. So from here to forming that kink, it's all that reorganization, and it starts deforming typically around 45 degrees here in these zones that are amorphous between crystals, and then so that's easy to activate. And then eventually when you really want to start to break down the crystal, you have some hardening, but it's not enough to prevent the deformation. So this deformation will grow to somewhere of the order of 400%, just like that, and then stabilize again. It limits your ability to really understand the stress-strain behavior of the material itself. When you run the test, you just get the overall response. And what happens a lot of time is when you start making your polymer more rigid, so at one point you don't have this anymore. It won't become stable. It's going to snap after forming a neck. It doesn't mean that you really change your ductility by a factor of 400 or whatever it is, because you change from 600, now you're at 20% elongation. It just means that somewhere in the high deformation range, it doesn't harden as much as it used to. So there's a lot of limitation in terms of looking at the stress-strain curve. In this slide, that's what I was talking about starting to deform here in shear between the crystals. So you start stretching them first, and then eventually they break down and reorient. There's a risk there if your load is too high in all this process to start forming voids and breaking out. So it's dependent on your pressure. All the formation of small cavities is a completely separate process that's more influenced by pressure. And here we're more talking about the flow inside the microstructure. Yes? Yeah, so say this is a cross-section of the spherulite, and then you start deforming it, and if you're going to form void initially, they'll form in this zone here because you're really trying to open up a relatively flexible amorphous zone between two rigid pieces. It's an adhesive joint with that respect over there. So how does deformation actually take place? I think is something you may want to know, either to understand the mechanics or to be able to develop your own theories here. I'm glad we talked about it already, that you have an elastic behavior. So if I'm taking this tube here and I apply a shear load, there'll be some movement. And these intermolecular bonds are relatively low energy, and that's why we have a lower elastic constant for the plastics. The carbon-to-carbon bonds, though, are really, really strong. They don't change distance. So the reason why you have a low modulus is the movement of one chain with respect to the other. What happens over time in this situation, we have the stress relaxation. So I applied a load instantly, and then all of a sudden, my polymer, the side groups that we were talking about, whether it's just hydrogen, whether there's a carbon group there, they'll be able to twist under thermal activation and get me that viscoelastic response. So it doesn't happen right away. You just need time to reach that condition. And then eventually, you can literally, if I had one chain here and the other there, they will flow with respect to the other. But that's a very slow and long process. So that's really what we think of it in terms of what happens in the material. A lot of people will try to think of it as springs. So the linear viscoelasticity, and you can go on and draw a lot of equations. It's good for understanding. It's good to understand that, like in this model, the standard linear solid, I can pull on it. It give me some elongation because I'm going to activate the two springs. And then all of a sudden, I'll have relaxation because this little dash pot here is going to elongate. If I release it, I get my elastic spring back, and then that's going to compress that spring a little bit. And then eventually it's going to come back to the original location. The biggest complexity with this is it's not linear. The more load you apply, there are more ways you can move around one molecule with respect to the other. At very low load, this is something you can apply a lot of times, but when you're really serious about getting percent strain in material in a relatively short period of time, you can't just neglect the effect of what's my stress level here in terms of how this spring is going to work out. Another issue is lots of time because you apply your driving force, it's a lot easier to get the viscoelasticity to deform the shape than to bring it back. So if you want to bring it back fully, you have to heat it up. That brings in the activation because the material will have a lot of memory, but because it's non-linear, what happens at high strain, when you let the stress go, what happens at high stress, when you let the stress go, is just not recovering on its own, and you need to heat it up to bring it back. So do you call it a viscoelastic or viscoplastic? It's really up to you. Ultimately, if you deform thermoplastics without changing the structure, like we talked about, obviously, if you go from a spherulite to the deformed shape, it's not coming back. But if you, at a strain level where it's really the movement of one molecule with respect to the other, the practical way to get back that exact geometry is to heat it up to recover the history. So we're going to move on and talk a little bit about other things that happens. Eventually, you form voids in the polymer. And so that's crazing. Stress whitening, if you take a little clip for the bread bag, it's got this color, and then you start bending it, it changes to white. It's because you're forming voids. So you're crazing in the material. It's very much related to what we talked about here, where there's an early stage of deformation that's easy to activate. If you happen to have it going on in multiple locations, you form these ligaments, and they become very strong, and it will hold small cracks together. So there's going to be a certain elongation, a certain release of stresses if you're at the tip of a notch, and you still don't really have a real crack, but you have a large area opening with a lot of bridges built up between them. It's related with temperature. So some polymers will show it at ambient temperature. Polystyrene is very notorious. Nylon, if it's dry, can form these crazes at ambient temperature. Polyethylene is too soft, so it's going to start deforming before forming voids most of the time, unless you go to a very cold temperature, and then all of a sudden it's brittle as well, like the other materials. So this concept that I was introducing to you between is it going to deform or forming voids, so the ductile or brittle behavior is applicable here as well. It's always easier to deal with a material that doesn't show a localized type of deformation. So if that's your goal, you need ductility. But if you're working with polymers, it means you're going to have to tolerate more creep. So there's that higher level of pitfalls with respect to having a low-strain alloy. It's not like steel. Steel, yeah, it will take less force to deform it, but at least it's not changing dimension until you reach the yield point. Here, if you make it softer, great, you don't have any crazing or any formation of void, but it will stretch over time and relax as well. So the spherulite, and this is essentially looking at the exterior surface of a semi-crystalline polymer, and you can see that the place where the crazing started was through the center of the spherulites because of this effect of having too rigid layer and a relatively soft layer between them, creating that tension condition to start forming the crazes. So if you have a faster cooling rate and your spherulite structure is finer, it's more intermixed, you have a thicker amorphous layer, you're going to increase that resistance. At the same time, most of the times your yield strength going down, and there are other characteristics that you sacrifice. So there's really, I would say there are more compromises in terms of mechanical properties with polymers than there are with metals. This is what happens we could be looking at the tip of a crack or at the higher elevation of these voids here. So if I have the material and I start forming these little voids, so I had two crystallites. These are the rigid crystal that we talked about. So they're very, very organized macromolecules here. I have the same here. In between them, I start having tension, and this is going to grow this way and this way until a certain point by opening up the system. You don't break the macromolecules. You just have to separate them. And it's almost always the case unless you really have a very brittle behavior. So the length of them matters. The higher the length, we call it the molecular weight. The higher the molecular weight, the harder it is to separate this molecule from this one. And there's almost no limit. With polyethylene, the higher you increase it, the better creep resistant you're going to get. At the same time, it's harder to crystallize it, but that's not always the issue. Here we're looking inside polycarbonate. It's kind of this is not a predominant way of failing, but it's shown in most advanced textbooks on polymer deformation because it's cool. So we don't have, in this case, with polycarbonate, we don't have any crystals. It's just an amorphous layer. So it's easy for the material, when you start deforming it, to continue to deform. There's really no significant resistance. In fact, we could say it will deform up to 200 or 300% until you kind of form this arranged structure locally. There's a lot of possibility. As you start moving, as you start deforming in an overload, you're increasing locally the volume in the material. So there's more mobility. It happens with bulk metallic glasses, which we haven't talked about, but it's the same principle. You open up the microstructure of the material, and now it's easier to move one piece with respect to the other. So that we're looking at a crack tip here. So from the crack tip, the highest shear is at 45 degrees. And when you start forming that shear, if the material just say, oh, I can do more because now I'm in an opening mode. You increase, you localize the deformation. We call them shear bands. They will happen in the volume sometimes with polycarbonate and other amorphous materials. When you're talking about semi-crystalline polymers, it's a lot harder because the crystal will interact with this and really make a block for it. So what do we do with it? We use a lot of polyethylene for piping. It's underground. There's still some aspects of degradation that needs to be taken care of. There are additives that you will put in polyethylene to make sure it doesn't degrade. So you don't think of plastics being completely inert to the environment. They do have interaction, a lot of interaction with the environment. They just don't corrode and lose section the way that most metals do. You have to run tests typically that last 10,000 hours, which if I remember, somewhere between 2 and 4 months, to decide on using or not using a certain type of material for 25, 50-year life. So every time you make a change, it involves a lot of testing to determine, do you create a betterment or did you reduce the life? And you have to be very careful because when you do these accelerated tests, you don't know if in reality it's going to be the same mechanism of deformation. So you're playing with saying, if I was just to increase the stress in deforming a polymer, I'll get movements that I cannot get at ambient temperature because I've increased my external force applied on the system. So most of the ways of testing for long-term polyethylene involve increasing the temperature. That reduces your load, and by increasing the temperature, it's a little bit like waiting longer for things to happen.